Hello everyone, my name is Ali Turani, and in this video I want to present our paper titled Towards Localizing Structural Elements, Merging Geometrical Detection with Semantic Verification in RGB-D Data. The point clouds generated by LiDAR or RGB-D sensors provide detailed spatial information, facilitating precise detection, localization, and 3D mapping of elements, essential for robotic perception and visual SLAM. In this context, RGB-D vision sensor offer a more comprehensive understanding of environments by fusing color and depth information. If integrated depth and visual information are provided, visual data captured by computer vision applications can form the scan environment into optimizable 3D scene graphs and depict their representations in multi-level abstraction models. Given the advantages of point clouds generated by RGB-D cameras, this paper aims to employ combined depth and visual information for geometrical calculation and semantic confirmation, respectively. The pipeline initiates with plane extraction using the depth data provided in point clouds of a given frame and completes with semantic label augmentation through processing visual data, resulting in rich information for building component localization. Accordingly, we introduce a real-time pipeline for accurate recognition and localization of building-level semantic components, that is wall and ground surfaces, a method for association and reassociation of the detected building components and representing them in 3D scene graphs, and incorporating the mentioned rich semantic entities to enhance the performance of visual SLAM through imposing environment-driven constraints. You can see the pipeline of the proposed framework in this image. Accordingly, the process begins with a sequence of video frames captured by RGB-D cameras, providing colored visual data and point clouds enriched with depth information. The point cloud and RGB-D data are passed to the geometric estimator and semantic validator modules, both running in parallel on separate threads. In geometric estimator, the goal is to investigate the points within the cloud to detect and extract potential 3D planes, that is, planar regions, present in the environment. If the point cloud contains noisy or low-resolution points, it can negatively impact subsequent processing steps. Thus, the point cloud undergoes a two-stage pre-processing procedure. The first step is to downsample the cloud to remove noisy or redundant points. Then, distance filtration is employed to only keep the 3D points that satisfy the depth minimum and maximum range. The next step is to apply the ransack plane fitting algorithm to detect potential planes with their geometric equations. Hence, sets of random points of the pre-processed point cloud are iteratively selected to calculate the normal vectors representing a set of geometric planes. The final output consists of the best fitting geometric planes representing all objects with planar surfaces detected from the filtered point cloud. It should be mentioned that the detected planes may correspond to the various objects, such as tables, floors, or screens, which are irrelevant for detecting building components required for understanding the environment's layout. In parallel to the geometric estimator, RGB frames are passed into the semantic validator module to extract semantic information, explicitly pivotal building components, including walls and ground surfaces. This module applies a semantic segmentation to label each pixel in the RGB data, ensuring that only relevant classes are kept while irrelevant entities are discarded. To do this, we employ a real-time panoptic semantic segmentation framework titled YOSO. Accordingly, each frame passes through the semantic segmentation function to make the semantic label map with a semantic class label for each pixel in the frame. Then another pass of ransack is applied to filter out noisy and incomplete parts, considering an uncertainty parameter. The outcome represents all planar building component objects derived from the RGB-D data, which may suffer from the sparsity due to segmentation resolution and occlusion constraints, making their geometric equations inconsistent. The geometric planes estimated by the geometric estimator are more trustworthy due to being derived from dense point cloud data, delivering accurate geometric analysis. However, they lack semantic information and can belong to any semantic entity with planar surfaces. Conversely, the planes determined by the semantic validator contain semantic labels belonging to a specific building components but lack precise geometric equations. Hence, the final stage of the pipeline involves associating these two variants of planes belonging to a given frame captured at time t, enabling the validation of the geometric planes and assigning accurate semantic labels to them. This results in semantically validated frames containing geometrically accurate and semantically meaningful data. The post-processing of the validated planes contains the dangling planes removal function to omit any plane that do not correspond to wall or ground surfaces. The remaining valid planes are passed through a structural validation function, ensuring that they satisfy the necessary geometric constraints for the environment. For instance, ground planes are constrained to be horizontal in the global reference frame, while wall planes must be vertical and perpendicular to the ground surfaces. We evaluated the proposed pipeline from two different perspectives using standard and in-house datasets. You can see the characteristics of the employee datasets and the device to capture the in-house dataset in this picture. To showcase the effectiveness of the proposed approach within a visual SLAM framework, we integrated our pipeline equipped with IOSO semantic segmentation into ORB-SLAM 3. The integration detects and maps the defined building components, in this work wall and ground surfaces, adding additional constraints while preserving the system's real-time performance. The evaluation results are shown in this figure. The baseline and its pipeline integrated version were executed across 8 iterations on the datasets to ensure reliable outcomes. As shown in this table, the pipeline integrated version outperforms the baseline across various environment layouts in most cases. This improvement is primarily due to incorporating environment-specific constraints derived from accurately detecting building components, including wall and ground surfaces. With such constraints, the system achieves a more structured and informed reconstructed map, reducing trajectory estimation errors and better aligning with real-world features. The table shown here presents the performance of the proposed approach in accurately detecting building components across different datasets. In this context, a true positive represents a building component that exists in the environment and is correctly detected by the method. A false negative occurs when a building component is incorrectly detected where none exists, while a false positive indicates a failure to detect an existing component. Accordingly, the proposed method's performance was assessed using object-level precision, recall, and the F1 score calculations. We can see that the presented method functions satisfactorily in most scenarios, consistently acquiring high precision and recall over various dataset instances. The good results are attributed to the integration of geometric detection followed by semantic validation, improving the accuracy of structural elements in the environment. Slight deviations in performance may occur depending on occlusions, the complexity of the environment, or incomplete data observation in the semantic map. On the other hand, several factors can be attributed to the causes of inadequate precision or recall results in some cases. A sample is an incorrect association between geometric and semantic entities due to fast camera motion during data acquisition, leading to tracking loss or visual feature mismatching. Additionally, curved wall designs pose challenges on association and validation, as the method mainly relies on planar surfaces for building component detection. Here you can see some of the mentioned limitations of the proposed method in challenging scenarios. As a continuation of the work, we are currently working to incorporate the proposed method into a real-time visual SLAM, empowering it to detect high-level structural level entities and perform semantic loop closing.